Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Dr. Hal Aldridge. He's the Director of Engineering from Cypress Electronics. His topic today is Trusted Computing and Security for Embedded Systems. Hal?
Hi. Hello, everybody. Thanks for coming today. I appreciate it. I hope I have an interesting presentation for you today. One of the things I'm going to try to talk to you about is maybe a different way, application area for cybersecurity. A lot of you are working in a lot of deep thoughts on network security, computing security against malware, and other things like that. But this is a slightly different application area and also a slightly different way to look at some of the challenges of cybersecurity as the threats evolve and some of the new attacks are coming out. But first, quickly, a word about who Cypress Electronics is and what we do. We're a company located in Tampa, Florida. We build a lot of cybersecurity devices for encryption, key management, and other applications, largely for the defense community. We've been doing it for a long time. We've been doing it for about 40 years. We've got 300 plus people in Tampa doing interesting work in that area. We also do a lot of electronics manufacturing. But one of the things that we're doing is also outreach to a lot of different universities. We have affiliations here with the CERIAS group for cybersecurity, at Carnegie Mellon, Scilab, and some other places. So you'll see some summaries of some of the research that we're doing here and other places as part of the presentation. So let's talk about what embedded systems are and why they're important to you. Embedded systems are a slightly different class of computing systems. They're not the desktop computer that's sitting on your desk or the server that's sitting in a rack somewhere. These are the computing platforms that are deeply embedded into devices. They can be anywhere from the controller on the engine of your car to the generator on a power plant to, if your coffee maker is programmed to come on at 8 o'clock in the morning and brew coffee for you, there's an embedded system in there that's doing that. They also have some interesting features. Historically, they've been very highly optimized, very cost-specific things that go into devices. So they aren't the large amounts of horsepower that you would need to do general-purpose computing on, again, say a laptop or something like that. They're optimized down. A lot of applications are still using 8-bit microprocessors, are still doing what they can to do things as cheaply as possible because as we'll talk about the size of what some of these things have grown into, you look into a modern car, there are 30 plus microcontrollers distributed throughout the car. So that adds up over time, and your cost of your car gets more. So that's an issue. They're also traditionally they've been very isolated, and we'll talk about those assumptions and how some of those are breaking down. But the idea being that I don't have to worry about a cyber threat because I'm not connected to a network anymore. That's something that's been an assumption in the past. There's also a lot of these out there in a lot of applications. If you start thinking about things like power grids and so forth, they've been in place for 20, 30, 40 years, and they've been running continuously. So there's a large embedded base out there that is now possibly open to cyber attack because the assumptions that were made in the beginning that there wasn't a security issue aren't valid anymore, and B, designing any security into those systems when they were built, since there was not seen to be an issue, they're kind of wide open. They also have an interesting property that, whereas if you have a desktop computer or something that has malware or something on it, if you need to reboot the system, you can reboot the system, and if it's offline for 5-10 minutes, nobody cares. But here, you can't do that a lot of times. These controllers are running a nuclear power plant. They're running any other type of application where they have to continue running. So now when you start thinking about those assumptions that were in the past of, hey, there's no cyber attack that can get me, now assuming that you can address some of these things with a cyber attack and they're vulnerable, now what do you do if you actually have a problem? What do you do to maintain operations? And also some of the roles and uses of these things are changing. Used to be these were just purely an item that actually ran a device or something like that. So there wasn't a lot of interaction necessarily with a user or somebody who's actually putting their personal data into this device. Now those are changing. For a smart grid application where this is running in a meter that is, say, looking at the energy consumption in your house, now there's privacy issues. Because if I can look at the plot of the energy that's being consumed in your house, I can tell when you're cooking dinner, I can tell when all the lights are off in your house, things like that. So there's some significant privacy issues now. So it's not just security, it's privacy. Similar to that, if I know the GPS location of the GPS in your car, I can say where you are, where you're driving, and so forth. So there's some issues like that that weren't ever intended to be an issue for embedded systems that now really are an issue for embedded systems. So another interesting challenge here is that the embedded systems are growing in their complexity, and we'll talk a little bit what that means to code in a moment. But the idea here is that if you start thinking about the embedded system that's running your coffee maker, that's a lot different from the embedded system that's running a smart grid for power control, or an unmanned aerial vehicle, or an unmanned ground vehicle. That is a real complex set of computers that are doing everything from computer vision to navigation to flight control and so forth. So that's interesting. And also, again, these folks, even though they're doing new control systems here with very complex applications, the actual thoughts of how you write security into them is really an afterthought. I know that because in a past life I actually was a robotics guy. So I actually wrote a lot of the control systems that went into some of these things. And I know that what I know now for security never got into those systems. And that's really just continuing to be the case. As you guys are talking about the concept of bolting on security after the fact instead of baking in the security while you're designing it. As these systems get more and more complex, it gets harder and harder to bolt on after the fact because it's just so complex to be able to catch all the things that could be a problem and as an afterthought, get to the point you can't do it anymore. Another thing that's interesting is the concept that encryption will solve all. If you talk to a lot of these folks that are doing these systems, they're saying, oh, well, all my data links are encrypted, so I don't have to worry about it. Well, folks that are thinking that way violate one of the main assumptions of encryption. The assumption of encryption is that the systems on both ends are trusted and they are free of viruses, malware, anything else that could be compromised them. If one of the ends is compromised, then the encryption really doesn't matter because you can put anything on the data link at that point. So that's something that folks can't get over that hurdle. But still, a lot of folks think as long as I'm encrypted, I'm safe. Also, recovery of the systems. Not only do you have to figure out that you have a problem, but you have to figure out, well, now what do I do? To my conversation earlier that I said that you can't just reboot and move on, how do you actually continue operations? So if you think about it in an autopilot for a system, you don't want to reboot the autopilot to your aircraft at 30,000 feet and just hope it reboots by the time you crash. So it could be bad. Let's talk about perimeter for a moment. Again, going back to the traditional thoughts about cybersecurity that, hey, now I've got a firewall in my system. As long as I'm behind the firewall, I will let it save me. That firewall will keep out all the bad things. It will check out to make sure there's no viruses that can get in and so forth. There's still a lot of folks in traditional computer security that believe that is still the case. So, as long as my firewall is good, I don't have to worry about anything. But just in the general problem, that's no longer the case anymore. There's so many threats for insiders that the enemy's already inside. So really the focus has shifted now to how do I have cyber resiliency? How do I continue to work through a attack, not just saying I will never be attacked. But that is getting even harder to get across that fact to the folks that are doing embedded systems. One of the main assumptions that got folks through the embedded system security challenge was the thought process that, hey, I'm not connected to anything. There is an air gap, physical air gap between the network that's running my system and the outside world. So there's no way that any bad code or anything can get across the air gap. Now, if you look at Stuxnet and some of the other attacks out there, I'd encourage you to look at Symantec's website. They've done some really great work on that and other embedded system attacks. Those air gaps don't exist. There are ways to get across them. The classic thumb drive examples of somebody took a thumb drive from a connected network to an unconnected network. Somebody took actually had a really complex installation at a plant somewhere, and some well-intending IT person cross-connected networks because they needed to do a checkout, they needed to update some software or something like that, and just forgot to unhook it. That sounds like a degenerate condition, but that's actually the real world. So you can't rely on having that perfect separation. And once there's a breach in the perfect separation, then really, anything is possible. There's also the issues of complexity. Again, that's the the big network issue that I just talked about, that you can't really confirm that as a system gets so complex and so many people are touching it, that all your security can be in place to preserve the air cap. And really sometimes it gets to the point that the air cap, just from an operational point of view, isn't feasible. I need to get this data out. I need to get data in. I need to know what for a power plant, I need to know what the planned consumption is for an area, or what the current state of the network is, so I know how to dial up my plant and dial down my plant to provide the electricity for an area. So somehow you got to get the information in. So you're kind of at that point of saying, hey, well, the air gap doesn't serve my operational needs, so now if I don't forget I had it in place earlier for a security need, then it's a problem. So this is just one of the assumptions that have gone for embedded systems, but this is one that I think ties nicely between the evolution of security in the traditional network and computer security world going over to the embedded systems world. So let's talk about complexity of embedded systems, and this is interesting. If I mentioned earlier that a lot of embedded systems traditionally and currently are still running on 8-bit microcontrollers. The lines of code are tens, or not tens, but hundreds. I mean, think again my example of your microcontroller that is in your coffee maker. If that's got a million lines of code on it, somebody probably wrote it in Java. Oh, sorry, bad joke. Somebody probably wrote it in something that they shouldn't have written in the first place. So there's not that many lines of code. But then you start taking a look at what are real examples of embedded systems. For flight avionics systems, there's 3 examples here from the 2 military examples and a commercial example. You're looking at systems with millions of lines of code. So how do you actually verify all that code is running and good? The interesting one there I like the most is the luxury car application. Remember I mentioned earlier that cars have 30 plus microcontrollers running around the systems. And if you look right now, believe it or not, I think the example they used here was one of the high-end Mercedes-Benz cars, that there's actually 100 million lines of code running on that car. Now, a lot of that you say, well, that's not critical. A lot of those are running my entertainment system, are running something that is not actually critical to the system, that's going to control the brakes on my car or the steering on my car. But that goes also back to the complexity argument that I talked about earlier. You remember the point about having that well-intentioned cross-connection that was there? As folks actually start thinking about the applications, like it would be interesting if my GPS could talk to my engine control system to tell me what altitude or something that I'm at, to adjust that for the best possible performance. Now I've just cross-connected systems, and if I create a vulnerability, I don't know, but I've definitely increased the complexity of stuff as a security architect I have to analyze and deal with. So there's stuff like that that's interesting. And you can kind of see some of that as you start looking at what's happening to the mobile computing industry, because I think it's a good example, because a lot of those applications started off with a lot of the same constraints as a traditional embedded application. I've got a small processor, it's going to run a limited amount of code, so forth and so on. But as the mobile computing has, the applications have increased and also the capabilities increased, you start seeing things are getting more and more like general purpose computing. Anybody got the real expensive smartphone recently with multi-cores and X number of gigahertz things and so forth? Anybody spend all the money on that recently? No? But they're there. And that, if you look at the folks that are as old as I am, which is kind of, I hate when I say that because I am getting old, the concept of this mobile phone was as powerful as the desktop computer was 10 years ago, 5 years ago. That's all true. So a lot of the things that you had that were attack surfaces 5 years ago, 10 years ago, that may now have been fixed in the traditional desktop and server computing world, haven't been fixed yet in some of the embedded applications, but you've got the same attack surface. So the Android operating system is 11 million lines of code. It's one thing to figure out how to have an embedded system that a lot of those didn't even run an operating system. Now I've got an 11 million line of code operating system that I'm going to drop on here and actually try to figure out how to do the security on. So that's an interesting thing. And also the increase in cyber attacks. Folks now finally start talking about, hey, how do I put antivirus on my phone? So that's coming, and it's just going to get, as we transition really the way the world is going, and everybody's seen the the discussions about the transition from the desktop environment to everybody's going to be mobile, and that's the trend, and the desktop computers will go away. So all those cyber attacks that were happening to the desktop computers and the traditional networks are now going to migrate over to the mobile devices and so forth. So if once it gets to the mobile devices, it's a short leap to take the same technology over to the embedded system world. So it's a natural transition there. So let's talk about some concrete examples. And I mentioned I would talk to you about some of the work that CERIAS is working on with some of the universities. This one is specifically at the Aero School here at Purdue. Professor In-Sak Wang is the PI. The idea here is what happens when you actually want to design a secure unmanned air vehicle. So some of the motivation here is you start looking about how complex this application really is. It's not just the actual flight control system that's flying on the aircraft. It's the interaction with that flight control system, with the ground station, with all the other data links, with all the other things in the environment it has to deal with air traffic control, with the communication. And also these things could be have tasking for multiple remote users. Some of those users may be interested in a video feed. Some of those users may be interested in controlling on the sensor. So these end up being, instead of these special purpose things that's just going to control an airplane to go from point A to point B and land, which is complex enough. Now this is a general purpose, almost server in the air in some applications to generate data and also interact with a lot of different networks. So all those things that we talked about earlier about embedded systems, the air gap and so forth, even though this physically has an air gap since it's actually flying in the air, the actual logical air gap there doesn't apply anymore. So they are vulnerable to cyber attacks. And also to my comment earlier about the concept of just embedding encrypting the data links isn't enough. This is where, as long as either the ground station gets compromised or the UAV gets compromised, doesn't matter if the link is still encrypted. You can still have bad things happen. So one of the tasks on this project has really been to separate look at the different components of a traditional UAV control system, and actually start separating them. And some of the things you see in the different globs here, some of them are almost kind of, I call them traditional computing functions. So they're the actual computers that are doing planning, that are, say, looking at machine vision, that are controlling communication with another site, that are actually reading data from a sensor. Again, you can almost think of this as if you put your mobile phone, put wings on it, and launched it. And actually, it's kind of some cool application if you want to look on the internet of folks actually building UAVs around mobile phones. Because interestingly enough, they have computing, communications, and all that stuff built into a nice small package that you can actually lift with a small UAV. But so there's that part of it, which is really more of the sections that are circled in green. If you look up here in these sections here, like this is circled in green. There's the other parts here that are circled in red. Now these are the more traditional controller specific applications. And by controller here, I'm talking about the embedded computers that are actually doing the math behind keeping the device in the air. They're the ones that are figuring out how much to move the ailerons, how much to move the rudder, how much to turn up the throttle on the engine, things like that to keep the device flying. That's where the traditional, and this is where some of the embedded systems applications really grow off and go into their own versus some of the traditional computing applications, in that there's a real world effect that the computers are doing in real time. So if I do something that says that I'm going to cause an aileron to go in the wrong way or cause a sensor reading to be bad, there's a physical time constant that you're dealing with. And if you don't do something correct in that physical time constant that it takes to go from 1,000 feet above the earth to 0 feet or -2 feet above the earth, bad things happen. So that's really some of the things that we're fighting with here. And also there's the interesting part about actually having that math-related piece there, which brings in a different discipline into the security analysis. So now you're not just talking about the computing side of the architectures. Do I have a stack overflow? Do I have a memory leak or something like that actually causes the computer to have a problem? Now I could actually almost make the math have a problem. Can I start doing things with the inputs to the math or doing things with the math itself to actually change the performance of the system? And we'll talk about that a little bit, what the effects are in the next few slides. Here's a nice specific one here. This is what happens, the thought process of I have a controller in the system, and if you start looking at the math and how these controllers are designed, since they're running on a system that is a discrete digital system, a lot of the theoretical control techniques that you design stuff with are considered to be continuous. But once I discretize that, then I have to pick a time constant that I'm working with. So I have to assume that I'm going to execute this control loop at 100 hertz, a kilohertz, or something like that. Once I make that assumption, then I can do my control design in such a way that I can ensure the stability, performance, so forth and so on. But if I can, as an attack, if I can violate that assumption, if I can do maybe something the equivalent of a denial of service attack on a controller in the system, so that they can't get their updates at the predicted rate, that they say that they can only, instead of the design point of, say, 100 hertz, I can only update at 50 hertz. And I've changed the performance parameters of the system because the assumptions I made in my control design are now violated. So if I'm assuming I'm an attacker and I want to do that, then this is now a attack surface that I can start looking at. And the interesting thing about that is if I know enough about the system, again, going back to the thought process of whenever you're an attacker on a system just in general, if you're just going to design a specific piece of malware that's going to go against a vulnerability in the system, you need to know about how that system, what software is running on the system, how that system is configured, so forth, to have a successful attack. Similarly here for an embedded system and something called the control design that you're going around this, you identify the parameters of the plane. You're basically saying, I know it has these flight characteristics, I know it has, it's going to perform this way. If I have access to the system, and now I know how this system operates, I can actually start saying, okay, I know that if I can make this go from 100 hertz update to a 53 hertz update, that actually crosses over the stability boundary of the system, and I can make a bad effect happen. So it's not just I'm shooting in the dark of saying, hey, I can just start doing something to the system. I can actually start making an intelligent decision about the system, knowing how it's performed to get the effect I want to as a malicious attacker. So again, this one's interesting because it takes it a little bit differently. You see the cool plots here and so forth. I don't think anybody's seen a Bodie plot in a CS class in a while. So, it's interesting. Shout out to all the ECE folks in the audience. All right. So, here's one that applies a little bit to maybe the thought process of folks that have been dealing with traditional malware and other attacks. Fuzzing. The classic fuzzing attack is in computer security is you just start hitting a function with random inputs and see where it breaks. Because a lot of the folks that design some software make assumptions about how the inputs to a function should be, and if they haven't done all the traps of making sure that the inputs are within limits and other things that are the good security coding practices, then you can see that you can actually break that. And once you break the system and cause that function to act differently, then you could have not only a vulnerability, but you could have an exploitable vulnerability. So that's the traditional computer science, computer security aspect of this. But if you start looking at it in what happens to a control system, there's a similar assumptions that are being made. Most of the folks that design control systems for a living who aren't thinking about security are really trying to fight Mother Nature. They're trying to make sure that I'm going to design a controller that's robust enough for what is considered generally a Gaussian set of inputs. So it's basically a regularly distributed set of noise that I have to deal with on my real inputs because no sensor is perfect. It's going to have some noise on it. So what happens when I have to deal with that, or I have to deal with a small error somewhere and my robust controller has to be able to handle that and keep me flying? That's how they're designed. So if I take that and I start instead, say I have access to a compromised system, and instead of sending the real data from a controller, I just start sending a completely random set of data, or a set of data with some interesting characteristics of that data that I think could cause a problem. But in general, we'll talk about just a random set of data here. If, again, same type of assumptions that I talked about for the classic cybersecurity application of fuzzing, but here I'm actually trying to drive the system to an unstable state. I'm trying to say instead of getting that point of view we talked about for the cybersecurity, I'm trying to get a page fault or something like that will give me that could give me root access through an exploitable vulnerability. Here I'm trying to say, well, what sets of inputs could I send to this thing to drive the controller unstable? In the beginning, I may not know. So the fuzzing aspect here, I'm just going to start sending stuff to this thing and see what happens. And the interesting thing about this is sending this random data to a controller that's attached to a physical system, in a lot of cases, is how you actually identify the characteristics of a system in the theoretical control sense. So a lot of times I'll have a physical plant that I will not know exactly the mathematical model of. So there's techniques for systems identification that in a controlled, not just a random, hey, I'm actually flying now point of view, but in a controlled situation, I can start doing some of this to generate some of those mathematical parameters of the system. So not only through this situation can you get to the point of just sending random data and see what happens and see if I can get stability, I can actually do this in the point of view of I want to learn about the system, I want to see what's happening. So again, to my point earlier about knowing what you're attacking, you can actually use this to start generating the ways to attack a system. So again, I think this is a nice overlap between traditional computer security and how it applies to embedded systems. So switching gears for a little bit here, let's talk about what trusted computing is. Now, I always put this slide up to make the computer scientists in the audience mad at me. I also love doing this at ACM conferences. So what do I mean by this? I'm saying software is evil, complex software is more evil, and then complex software running on a complex operating system is even more evil. So of course I'm stretching the point there, but the thought process is the bigger the piece of software it is, the harder it is from a security point of view to analyze what all the vulnerabilities of it could be. I mean, think about having 10 lines of code running on a bare processor. Then hopefully, if I know what those 10 lines of code are, then I can figure out that yes, those 10 lines of code, there's nothing that can happen to the system. I can send any input to it, any output from it. It will just execute those 10 lines of code. Now, if you go to the other extreme, the luxury car example I gave earlier, we've got 100 million lines of code running on a distributed system that could have several operating systems and so forth. How do you actually do the security analysis to say, yes, that's actually a secure system that's safe and stable for me to drive my car around with? It's tough. So one of the interesting ways that folks are trying to tackle that problem is through trusted computing. Now, the idea of trusted computing is that you're going to combine a hardware unit, and we'll talk about what that hardware unit is in a moment, with simple software to provide a secure computing environment. My simple software here, I'm talking about a something that's tractable. It may not be tens of lines of code, but it's not millions of lines of code. And also, it's probably specific to a task that you're saying now, instead of running a task that I need a general operating system for, I'm going to check a specific value in the system, or I'm going to confirm that the hash of a specific file or something is this. So something that's tractable that can be done there that can be something meaningful. And that's really the idea of keeping that amount of software low is the concept of limiting the size of what's called the trusted computing base, and that's the software there. Now, some interesting technologies that allow you to do that. A lot of those are more specific to the desktop and server type environments, the traditional environments than the embedded systems environments, but you'll see that's trending a little bit differently. One of those is the trusted platform module that I'll talk a little bit about. It also has some interesting things that are on modern processors now that work with a TPM that allow you to do some interesting things about switching back and forth from a secure world and a normal world and things like that we'll talk about a little bit there. But if you're interested, if you look at the Trusted Computing Group, they're a entity that's been around for a while. They did the initial specifications and continue to maintain the specifications on the TPM. A lot of companies that you've heard of there, from Microsoft to other places to companies that you've never heard of before today, like Cypress Electronics, are all members of that group, and we're actively pushing the standards in those areas. So let's talk about what a root of trust is, because it's one of the fundamental pieces of a trusted computing environment. Fundamentally, a root of trust is some point in the system that you really believe is going to operate in a way that you think it should operate with a high level of assurance. So it's this one little piece that everything else in the system may not be trusted, may not be secure, and so forth, but with some really good thought process, because you've done the security analysis and so forth behind it, that this little piece of the system is something I trust. So the nice thing about that is you can start taking that to the next level and extending that trust up the chain of trust. Before I get to that, let's talk about the difference between a hardware root of trust and a software root of trust. Now, you can do either. They're both valid. But there's some advantages to having that hardware root of trust in the system. And by that, I mean it could be a chip, a fundamental piece of the system that is not directly tied to the main processor on the system. It could have some physical hardening of attack. So if somebody actually got physical access to the device, it may be able to do some level of protection of some key data. Also, it has a little bit better capability to be insulated from a software attack. So say that there is a separate chip on your motherboard. It could be a root of trust or whatever, but say there's another chip on the motherboard of a computer that you were trying to attack. It's a lot easier to get access to the Ethernet chip and the main processor. It might be harder to figure out how to get an attack to a chip that's on another board somewhere else in the system, especially if that chip on the other board in some place in the system actually has some security features on it. So you're actually putting another level of isolation in the system. And that's different from just another process that you might be your software root of trust that's running on the same computer, maybe even under the same operating system as the rest of my code in the system. So the harder that you can make that root of trust, the more hardened you can make that root of trust, the better that you can actually implement a trust chain. And the idea behind a trust chain is going back to the concept there that there's one little piece of the system that I really, really believe in. So now can I take that one little piece that I really, really believe in, let it check the next level of complexity up in the system. Let it check that file that I want to make sure that all the data in that file was the way it was originally intended to be. So I know what the checksum, the hash, whatever that file needs to be. So I'm going to let that little piece of hardware root of trust perform a very simple operation and say, yes, that actually is what it is. And by the way, I'm going to send that message out the system and to somebody who cares to make sure that this system is running the way it should be. And I'm going to do it in a cryptographically secure method that says, hey, yes, I am who I am. I checked this. I was the only thing running on the system at the time, or I was isolated from the system. I checked it. It's good. You can trust that level left of the chain. And you can start extending that over time. But like all chains, it's only as good as the weakest link. If you say that for that same example that I just gave, it's one thing to check the hash of a file, a small file. It's another thing to say, I'm going to check the hash of the Android operating system, and I'm going to check it with the dynamically linked events, and I'm going to check it with the 5 apps that are now running on the system. And not only now is it something that is a lot of variation that I may not be able to predict, but also it's a big thing to do. So again, it's going up the chain there and actually trying to make sure that you're, as a security architect, you feel that your chain is going to work for you. So here's an example of root of trust. This isn't the only one, but it's the publicly available. It's one of the publicly available ones. This is a trusted platform module. If you're interested in the specification, it's one of the Trusted Computing Group specs. If you have a high-end desktop computer, a high-end laptop, a server, it's a 90+% likelihood that you've already got one of these on the motherboard in your system. There are 300 million plus of these currently in the field. There's another interesting discussion that I can do another lecture somewhere about why only a few percent are used, but that's another issue. But really, the goal here is to talk about some of the internals of things that could be in a root of trust. You see some pieces here, a lot of cryptographic features from SHA, which is a hash, to the key generation, to random number generators. There are places that you can hold specific keys. Like up here, there's an attestation identification key. We'll talk about some of the applications of this device in a minute, but one of them is to be able to keep a cryptographic key separate from the rest of the computing in the system, so there's not a chance of that cryptographic key being compromised and sent off the system. There are also things like platform configuration registers, which will allow you to store data on the system. These could be, I mentioned, say, the hash of a file that I talked about earlier. It could be that you would be maintaining the hash of a file over time. A lot of different applications there. There's also the ability to actually execute small things in here. So say that you wanted to execute a small task that was going to execute the SHA of the hash of a file. All that stuff could be done on the TPM and not have to be done on the main processor of the system. So, and this is in a package again that's separate on the system, has some basic anti-tamper and other things for it. But really the key here is to say that this is a system with a specific set of capabilities that can not only perform the functions but can actually have some cryptographic goodness to it that says that when I actually want to report on this, that it's not just a generic piece of data coming back, that the report could be coming from anywhere. It's actually coming from the system that should be doing the reporting. So let's talk about some of the applications for trusted computing. One of them is a secure boot. The idea being that I'm now going, before I actually boot a system, I'm going to confirm that the image that I'm booting from is what I thought it was. That has a lot of good applicability to make sure that that no change has been made to the operating system a priori. So say that somebody has come into a system and has connected a test device or something to the system between the time it left the factory and the time that it was being used, and that system actually changed what the operating system that was loaded. So now this is a way that you can have something independently checked before the system actually runs to say, hey, this is the operating system, if the hash is correct, whatever other features I want to correct is good. Attestation, this is the concept of measuring a system value and communicating it back to a validator that's actually going to say that, hey, yes, I got a response. This system can join a network. For give an example being say a meter in a smart meter infrastructure could, when it comes on, it may have to attest that yes, I am who I say I am, that I got the right operating system and so forth before it's allowed to join a network of other meters in a system. Secure world, there's a lot of ways to term this one, but the concept here is that I have the ability to switch between modes that a processor is running in. If you look at the Intel TXT extensions, and there's an AMD equivalent, that's actually the extensions on the processor that allow it to go from I'm running a full version, everything's normal, I'm running a full version of an operating system, to be able to say, okay, I'm going to dynamically switch off of running that. I'm going to clear everything out. The registers are cleared. There's no remnants of that operating system. I'm going to quickly do a specific function in a more secure environment, so there's not a possibility of there's an existing compromised system. That's all been cleared off. I'm going to be able to run in this environment, do something, and make an attestation or do something else as a result of that, and then I switch back seamlessly to where I was before. So that's really the key there. So that concept there is normal world and secure world. So normal world is where I'm doing my normal task. Secure world, I can go to another place. And that's useful to the concept of limiting the trusted computing base. The idea being that now my trusted computing base is what's running in my secure environment versus having to figure out how to protect the entire operating system. Also, the interesting part of key management, the idea there being that I really want to do some of my cryptographic functions in a different environment than I am for my main computing. If you think about the cryptography, most of the time you're not trying to protect necessarily the software that's running actually running the crypto algorithms, although there are some vulnerabilities there too. But you're trying to protect the key that's associated with the cryptographic algorithm. So if I just have the key available freely in the system, even if it's encrypted at rest, once it's loaded onto the processor, likely it's not encrypted at that point. If I have another process on the system that is malicious and knows that there's a cryptographic software running on the system, it may be able to know where the cryptographic key is stored in memory and be able to grab it off the system. So that's a significant vulnerability that the folks that design crypto systems have to work against. But here, in a trusted computing application with something like a TPM, then you can actually store that in a place that is hardened and separate from the main processor. So how do these things relate a little bit here? So the idea being that the trusted computing is a hardware-based, hardware and small software-based concept, which if you go back to my assumptions earlier, that having that hardware and small software-based concept was how embedded systems really start off. So when it gets back to its roots, then it's really a similar type application. But one of the problems, though, of making that leap right now is that applying trusted computing to embedded systems is a new area. It's not as mature as it has been for, again, the traditional systems. And some of the challenges there are really that there's no standard root of trust. So if you start looking at what is being used now, a lot of folks are relying on either trying to do a software root of trust or they're trying to do an application-specific root of trust, whereas that's all well and good, but it makes it a lot of one-off type of solutions. You can't just have a generic solution like you could have on a desktop system currently. Also, there's the embedded processors right now don't have all the features yet. I mean, even the x86 architectures that are out there for desktops, the low-end processors don't have some of the features I mentioned earlier of Intel TXT and those that actually can allow you to implement trusted computing functions. But the mid and high-level processors do. So if you start looking at the embedded processors, there's not a lot out there that have them. The equivalent of Intel TXT, roughly, although it's not the same because the feature sets are different, is the ARM processor families have a concept called Trust Zone, which can implement Secure World and some other features. But they don't really have the feature set. And to my point earlier about TPMs and so forth, they don't have a wide adoption in the desktop community anyway. So making that leap now, we're going to put it into a new application area and actually have those features along with the process-specific features. Then again, there's some issues making that leap. There's also an analogy in mobile computing. A lot of phones have a trusted computing function in them, but they're really targeted towards a different use model than what we would actually like as programmers and system designers. Whereas they are looking more to defend and protect the interest of the phone provider, making sure that there's nothing you can do to mess up the billing on your phone, so that you can't make a call and get it billed to somebody else's number, things like that. That's really the function there, not to protect the applications, to protect the operating system and so forth. Although it could, but that's not been the focus. So as that gets to more, and there'll be more adaptations of that into mobile computing in the broadened point of view, again with my point of view that there is a new threats to mobile devices now, so that some of the same reasons that we did trusted computing in desktops and so forth are now valid for mobile computing. Also, cost and reuse. The security of embedded systems, again, hasn't been a high priority. If the choice was to get 10 cents out of a system, or I add security for 10 cents more, traditionally the decision would be not to put the 10 cents in. So actually having that now, having a reason to put some of these elements into the system, both on a recurring cost of, hey, it's going to cost, I have to put this extra component on every board I build, and also the non-recurring cost to develop the systems, again, is a difference. So just a quick hit on some of the interesting research that we're doing in the general trusted computing area. We're currently working with a couple different universities, Carnegie Mellon and Purdue. The main one at Purdue currently is actually the PI here is Elisa Bertino. The idea being that we're looking at actually some of the software issues of how you actually look at, with a trusted computing system that has multiple cores, how do you take advantage of the computing on the multiple cores to look at it from a security environment, not just a code optimization or a performance optimization environment. And it's very interesting when you start going down that route that there's a lot of security things that you can take advantage of now if you start thinking of breaking things up over cores, especially if you start thinking have a large number of cores in some applications that say, everybody's buying a desktop system these days, you're going to buy a multiple core system, and those numbers of cores are only going to go up, and they're going to get cheaper. And even in the embedded applications now and the phone applications, you're now looking at multi-core computers. So taking advantage of the system really ends up becoming more of a software challenge than a hardware challenge. It's the same thing that folks have been fighting for in high-performance computing over the years of how do I actually optimize my performance over multiple cores. But now on this application, how do I optimize my security by using multiple cores? So there's some interesting work going on there. So just to summarize, when it comes to the points I kind of want to get across here are that embedded systems are everywhere. I don't want to count the number of probably embedded systems that are in this room or in this building. So they're everywhere, and now they're actually the subject of cyber attacks, and those cyber attacks can have real world effects on things. It's not just that my computer's down today, it's that my power plant's down, or it's that my plane is down, and so forth. Trusted computing is a way to leverage some of the inherent characteristics of embedded systems. Again, they're tight coupling of hardware and software that allows you to actually build a level of hardware-based security into the system. And also it's a good match from the types of computing that they do. It's a lot of times you can think of separating security critical functions in an embedded system that sometimes can be pretty obvious. They could be a monitoring function or so forth that you can think about doing in a secure manner with a trusted computing system. So just as a last pitch here, we are recruiting. So if anybody would like to move to a much warmer climate and a beach. See us. We're recruiting to Tampa, so we'll be around after the lecture. Thank you very much. Any questions?
I have a question, and if nobody has a question. So really, thank you for the nice talk. I have a question. I really like the slide where you talked about the challenges of trusted computing in embedded systems. But I have a question. So we know how to do attestation of software, but what about attestation of hardware? How do we do that? Is there a similar notion or
I think there is, but I think it's just going to that next level of reducing the parts of the system that have to do the attestation even more. There's a whole trouble with the possibility of trusted supply chains currently, and I'm using the word trust there in another meaning, but the idea of trusted supply chains is: do I know where all my hardware is coming from? Do I know where the firmware on the system was loaded? Do I know where the ASIC was burned? Do I know where the mask on the ASIC came from? All those pieces, which is an ongoing challenge. I mean, if you start looking at for a high security application, I want to buy components. Well, do I know where all those components came from? Can I control where all those components come from? I really can't. So to answer your question, I think it really comes down to actually keeping that trusted computing base as small as possible. And here it could be that I will have a very small section of a hardware device that I can actually confirm the way it works, but it will check a larger portion of the hardware device. But this is an ongoing challenge, and nobody's got a great solution for it yet.
What are some of the features that the ARM Trust Zone is lacking compared to standard computing desktop environments?
A lot of it is flexibility in how you actually deal with some of the memory space controls. I think is one of the big features. The ARM Trust Zone really mainly, the big feature of that, although I think there's a lot of other things, the big feature is really getting you from normal world to secure mode, secure world. The Intel TXT and other extensions, especially when you start mating it with some of their other extensions that are more specific to handling virtual machines and so forth, do a lot better memory separation and memory mapping in the process. They allow you to actually more physically secure at a lower granularity level the different memory sections in the system. Okay. But I'm not an expert in those areas, but there's a lot of documentation out there on them.
Okay, thank you.
Okay. All right, thank you.